Rotary encoders. They come in a bewildering variety of shapes and sizes. You can buy little kits of them containing knobs and retaining screws. I've got an old one there, don't know where that came from. This one has got no détente, so it doesn't click as you turn it round, it just turns continuously. And most of the others have a switch, so as you press them, you've got a momentary tactile switch there that you can press. They generally have a different number of clicks per turn, anything from 8 to kind of 24 is quite common, but they all work in essentially the same way, which is that they have some kind of common connector, and then they have two other connectors that they call normally A or B, and essentially by looking at whether A closes before B or B closes before A, you can tell which way the shaft is being rotated, and optionally, if you time those closures and openings, you can see how fast it's being rotated as well. So lots to play with. That's a nice little module. I might use that one because it's got breadboard pins on it. I'm just going to wire the encoder in here, encoder A, encoder B, and encoder switch. And what I'll do is have internal pull-ups and then switch them to ground. So there's a nice convenient little bit of pin-outery there. One of the problems with rotary encoders, and in fact all mechanical switches, is switch bounce, and this is a trace of a switch opening or closing, and you can see that it bounces several times before it arrives at the new level. One of the ways of dealing with this is to put a low pass filter on it, so the capacitor takes time to discharge and time to charge through the resistor, and during that time the contact can be bouncing away, but you end up with a slightly cleaner signal. There are several different software solutions around for dealing with switch bounce, such as resampling the inputs to make sure they're stable before deciding that's the current state. But I really like this approach. It's from a guy called Pinteric, and what he says is there are only 4 valid states for the switches to be in, the A and B contacts. They're either both low, which is called 0, 0, both high, which is called 1, 1, or 1 high, 1 low, or 1 low and 1 high. And these are the 4 valid states. So if you start off at 0, 0, if your next position or your next valid value is 0, 1, you must have gone anti-clockwise. You've gone backwards. If your next position is 1, 0, you've gone forwards. And it is not valid to go from 0, 0 to 1, 1, for example, because you've moved over the next valid state. And he shows this in a finite state machine. So if you're sitting at 0, 0, the only valid transitions are to 1, 0 or to 0, 1. If you're at 0, 0, you still stay at 0, 0. Transitioning to 1, 1 is an invalid transition. And so you've got these basically 16 different possible transitions from any one position, and only some of them are valid, clockwise or anti-clockwise. The other transitions, 1, 0 to 0, 1, 0, 0 to 1, 1, are invalid and therefore cannot exist. And he has implemented this. There's some C code for Arduino, and we can basically use this. This is Marco Pinteric's code, lifted pretty much exactly from his C Arduino code, but with the modifications suggested by Ralph Bacon, and I'll just show you those. The modification that Ralph suggested is, rather than poll the encoder inputs to see what's happening, just trigger an interrupt. So trigger it on either A or B, rising edge, falling edge, don't care, trigger an interrupt, and do your polling in there. So I'm only going and checking the rotary encoder when the interrupt's fired, and we'll have a look at what that does. Here's the encoder wired in. I've just wired in the A, B and switch pins across to the Raspberry Pi Pico plus a ground. I've just put a knob on it so that you can see me turn it a bit better, but if we turn it, turn, and back the other way, turn, we're getting very reliable, no bounces, indicators of clicks and indicators of direction. What do we do with the encoder then? Well, I have discovered that if I just change the global delay figure by a large increment, I get all sorts of small clicks and pops as the read pointer hops over various samples. So I've introduced something that I've called a target delay, and I am ramping the global delay towards it, either incrementing up towards it or decrementing down towards it, once every sample that we process. So in a second, I can ramp the global delay forwards or backwards by 48,000 samples. And I find that these smaller changes reduce the clicks and pops considerably. Therefore, under control of the encoder, I want to increase or decrease the target delay. And I don't want to do it by a fixed amount every click, because if the target delay is very small, I really need a very small increment. Whereas if the target delay is very large, you're really not going to notice one or two samples added or subtracted from the delay. So what I'm doing is looking at the current value of the delay and using a switch statement to calculate or to derive an increment value. So if the current target delay is 0 to 10 samples, I'm just going to increment or decrement by 1 sample. If the target delay is currently somewhere between 11 and 100, I'm going to add or subtract 10. If it's 101 to 1000, add or subtract 100, and so on. And so this means that as you increase the delay, it will take bigger and bigger steps to get to where you're going to, because you don't want to turn the rotary encoder 146,000 times just to advance the delay by a certain amount. You want it to go up in decent steps. So then, according to which direction we're going in, we're either adding the derived increment to the target delay, or we're subtracting it from the target delay. And I'm just printing out the result of that. So we'll just have a quick look at that. So I've just turned the delay down to 1 sample. So if I go up in increments, that's 2 samples, 3, 4, 5, 6, 7, 8, 9, 10, and then we start going up in tens, so 21, 31, 41, 51, up to 101, then we go up in hundreds, then in thousands, and this way we can very soon get up to the maximum delay and back down again without too many turns. Well, the $64,000 question, actually it's probably more like the £6.40 question, is what does it sound like? So here we go. So I'm down at a delay of like 1 sample. If I turn the feedback right up, and that is right up, there's not enough for it to feedback yet. Then we come up. There we can hear it. We're starting to ring it. Very, very short delays with a bit of feedback, so it's now we're getting into proper proper delay territory. Can turn the feedback down. So I can start getting into very long delays. There we go. Oodles of bouncy fun. I figured that if you got into this kind of situation where the delay's gone a little bit nutty, it would be helpful to be able to zero out the whole of the memory buffer to be able to start again. So I implemented a function to clear down the memory if you press the encoder button. However, it makes that horrible noise. So then I implemented the soft mute under program control. I've got the soft mute wired into pin 16, GPIO 12. And now if I zero out the buffer, you get a nice bit of silence before the delays start again. So I think that's well worth doing. And I've also, because we can clock the delay from the internal clock or an external clock, or run it in some kind of non-synchronized fashion, just using the rotary encoder as a delay knob, I've put in a switch to choose between whether we're running synchronized or free running, if you like. Yet another GPIO pin bites the dust. These are the GPIO pins I've used for that. I've got pin 26 for what I'm calling a sync-free switch. So that's normally pulled high internally and switched to low. And then this is the PCM 5102 soft mute. So under program control, I can mute the output of the Parrot whilst I'm zeroing out the buffer. And you know, this only leaves me now with 3 available GPIO pins. I could add a GPIO expander, an I2C expander, something like that, but I'm loath to do that because I'm trying to keep the component count reasonable. So with these 3 GPIO pins, I could, for example, add an 8-way switch, binary coded decimal, 3 digits. I could add a 4-way switch, and then I've got another GPIO pin for input or output or something like that. So I need to decide, really. I definitely need some sort of switch because I'm going to have to choose different reverb algorithms. At the moment I've just got a multi-tap delay, but presumably I want to implement a ping pong delay, maybe some sort of stereo widening effect. I don't know, I haven't decided yet, but the user needs to be able to choose something by rotating a switch. So I'm thinking at the very least a 4-way switch connected to these 2 pins, but maybe an 8-way switch by pulling in this pin as well. I need to give it some thought.